Hello, everyone, and welcome to the third session of Machine Learning Fundamentals and Introduction to Python course with engineer host Belyadi. My name is Jamila, and I am last year petroleum engineering student at French Azerbaijan University. Today, I'm your moderator for this session. First of all, I would like to introduce our special guest, engineer host Belyadi. He is a senior data scientist engineer at Wine Oil and Gas LP. Additionally, he is founder and CEO of Intelligence, focused on providing artificial intelligence in-house training and solutions. Mr. Belyadi has served as an adjunct faculty member at multiple universities, including West Virginia University, Marietta College, and St. Francis University. There, he taught data analytics, natural gas engineering, enhanced oil recovery, and hydraulic fracturing stimulation design. Mr. Belyadi has over 10 years of experience working in various conventional and unconventional reservoirs across the world. He has worked on various machine learning projects and held short courses across various universities, organizations, and the Department of Energy. Mr. Belyadi is the primary author of Hydraulic Fracturing in Unconventional Reservoirs, first and second edition, and author of Machine Learning Guide for Oil and Gas using Python, and also he has authored and co-authored several SPE papers. He earned bachelor's and master's degree both in petroleum and natural gas engineering from West Virginia University. Please don't hesitate to ask your questions to Mr. Belyadi regarding today's session in question and answer section. I will read them out in the end. In case of any problem, you can approach me in chat box. And now I ask you to give all your attention to our speaker. Mr. Belyadi, mic is yours.
Yeah, thank you so much, Jamila, and thank you again to Pio Petro and Ahmed and anybody who really put in a lot of efforts to organize these amazing short courses for students across the globe. So with that, let's get started. So yesterday, I had a very special guest on the podcast, Dr. Fred Aminzadeh, and we discussed a lot of important issues, important topics, including machine learning, deep learning, and natural language processing. So as I said, if you haven't subscribed to the YouTube channel, please feel free to subscribe to the channel. All the material is free. It's just for the intent of this podcast is just to provide free educational content to anybody who's interested in data science, in AI, and in the future of automation in the energy sector. All the materials that, like I said before, will be coming from this book. So with that being said, so last time we discussed supervised, machine learning, and we discussed one of the algorithms or techniques that we used that we use in supervised machine learning called artificial neural network. We talked about different types of the difference between AI, machine learning, and deep learning. Then we went into kind of a little bit actually in detail on math in terms of how you actually, how these neural networks are set and how they're actually calculated. And we talked about feed forward type of propagation, back propagation. We talked about activation functions. We went through an example together, if you recall. We went through an example from start to finish on if you train a neural network model, and if you apply, and if you want to predict future data that is coming in, how would you, do the matrix multiplication and apply the, add the bias, apply the activation function, and all those things. So I hope that made sense, because this is the fundamental of neural networks, and to understand other types of more complex algorithms such as convolutional and recurrent neural networks. You first have to understand basic ANN, and then we can, and then more advanced concepts will be much easier to grasp and understand. So I thought about today, I was like, what would be good? Because, the time of this course, this is like, a 4-hour course, from start to finish, and there's so much to cover, and there are so many different algorithms. So I was like, what do I cover today that would potentially help the students, benefit the students a little bit? And then I thought, okay, let's talk about, we covered ANN, which is one form of supervised machine learning algorithm. I said, okay, let's talk about an unsupervised machine learning algorithm as well. We discussed it. We said you have different types of unsupervised machine learning algorithms. If you remember in lecture 1, we said one of them is K-means clustering. Another one is hierarchical clustering. Another one is density-based, the DDB scan, type of clustering. So I just wanted to pick one. I wanted to pick one that is widely used in different industries and kind of go over the fundamentals of that and what it means. And just to show you an example of how this K-means actually works like mathematically, okay? So as I said before, K-means clustering is one of the most used unsupervised, remember, it's unsupervised machine learning algorithms. And if you recall from lecture 1, an unsupervised, machine learning type, it doesn't have a label. It's just, if you have a set of input features and no label associated with that, with those input features, you can use some type of unsupervised machine learning, unsupervised machine learning algorithm to cluster your data, based on like and so on and so forth, right? So one form of unsupervised machine learning algorithm is called K-means clustering, K-means clustering, okay? And K-means is actually a pretty simple technique, and I can share with you how it actually works mathematically. It's quite simple. To do it by hand, it takes some time, but if you use Python, it doesn't require actually much time and effort to write the code for applying K-means clustering within scikit-learn. And I'll tell you what scikit-learn is like towards the end of this lecture. So some of the application, you might say, okay, Haas, okay, this is K-means clustering. What are some of the applications of K-means clustering or unsupervised machine learning within the oil and gas? Well, one of them is called, we actually wrote a paper, it was a few years ago, on using K-means clustering for liquid loading. And basically what we did was we took, gas rate, casing pressure, tubing pressure, water rate, and line pressure. Okay, and instead of using, if you guys remember from your reservoir course or natural gas engineering course, and instead of using these traditional conventional techniques such as, for example, Turner and Coleman rates, we purely used K-means clustering to cluster the data into two different types of clusters. Cluster 1, which was loaded condition, and cluster 2, which is unloaded condition, okay? So once you have a model, once you have a K-means clustering model, and you have those cluster centroids, then you can actually, predict, what happens as you get more data, more information from your field, whether it would be cluster under cluster 0 or cluster 1 or cluster 2, based on unsupervised K-means clustering technique. So this is one application of applying K-means clustering, which is used for liquid loading clustering or liquid loading detection in other terms. The second application is, for example, if you have, as I said, if you have a lot of geologic features, a lot of production data and all those things that you have, and you want to cluster your data into different, type curve regions, into different areas of interest, So for example, I'm going to have, this is my map. I'm going to have this area of interest, this area of interest, this area of interest, and so on and so forth. You can also use some type of, K-means clustering or any type of unsupervised machine learning algorithm to for type curve clustering. This is another application of using K-means, K-means clustering. So let's look at this, for example. So the process for actually K-means is fairly simple. And so let's look at this. So basically, as you can see here, the first step in K-means clustering is initializing the centroids, okay? That's the first step. So let's just say you have an X and Y, and then you just want to just initialize you just say you want to have two clusters, okay? You just want to have two clusters. Let's just say you're trying to solve a liquid loading problem. And based on your domain expertise, you know that, for example, there are two conditions. One is loaded, one is unloaded. Or you could argue and say, okay, I might have more than, two clusters. I might have three clusters. I might have four clusters. And I can show you one of the techniques that you can use to determine how many clusters you need. But determining the number of clusters is probably one of the most challenging pieces within using K-means clustering. Because if you don't know how many clusters to choose, you purely have to go by, some kind of an elbow technique to determine when, adding more clusters would not improve your result of your model, right? So I would say if you use any kind of clustering, like especially K-means clustering, it is very important that you use your domain expertise to kind of start off with how many clusters you're going to need. You would probably need, depending on the type of the problem, you can probably guess that, but also you can use other techniques, which we'll discuss one of them today. It's called elbow technique to determine how many clusters would give you the optimum result. And to be honest with you, once you're done with clustering, one of the most important things is to visualize the data. If you apply your K-means clustering, always make sure to visualize the data at the end on a map or on anything that you're interested in, to make sure the clustering that K-means did makes sense, to make sure that the way the algorithm works and the way the algorithm works for that type of problem makes sense. And a lot of times you have to massage the data. You have to add more features. You have to add, for example, I'm going to take the log of that feature, or I'm going to do some type of mathematical, manipulation to the data to help the K-means understand and distinguish between different clusters. Anything that you can feed the model to help the model is good. It's not bad. So don't be afraid to massage the data, not change the data, massage the data, or add features based on the data that you already have to help the K-means, clustering. So let's just start with that. So let's look at the left-hand side picture, okay? So let's just say, like, this is a liquid loading problem, and based on your expertise, you're a production engineer, and we have two conditions. One, when the well is loaded. Two, when the well is not loaded, right? Or you can argue, say, Haas, I want to add one more. I want to say when the well is loaded, when the well is unloaded, and also when the well is semi-loaded. That's no problem. You can try to have more clusters. But just for this example, let's just make it simple. Let's say you have two clusters, okay? So look at the left-hand side picture. So I have two cluster centroids. One is in green and the other one is in red, right? So now the next step is what you have to do. You have to measure the distance. Measure the distance from every single point. You see these points, these instances? Measure the distance from every single instance to each cluster centroid. So I'm going to measure the distance from this instance to this cluster centroid, and measure from this same instance to this cluster centroid. If this instance is closer to this cluster centroid, then I'm going to assign that to this cluster centroid, which in this case it is, right? This instance right here is closer to this centroid as opposed to this green centroid down here. So that's why these, data points or these instances have been assigned to the red cluster centroid, and these instances have been assigned to the to the green cluster centroid. As I said, all you have to do is just measure the distance from here to here, and from the same instance to here. Go to the next point, from here to here, and from here to here. And simply, what kind of distance you use, there are different types of distance functions that you can use. One of them is called Euclidean distance function, which is the most commonly used distance functions. And I can show you the equations. This is pretty much you've had it back in your like algebra days. You can use Euclidean distance functions to calculate the distance from each instance to the cluster. So now, so now that you have assigned these these instances to this centroid and these instances to this centroid, the next step is to take an average of what is the average distance between the instances in each cluster. So what is the average distance between all of these instances in the green cluster, and what is the average distance between all of these instances in the red cluster? And then what you do is you move that cluster centroid to the average of these instances, and then you move this green cluster centroid to the average of these instances. And when you do it, you get this kind of figure. Okay, so new centroid computation and reassignment of instances. So now that you have moved the cluster centroid, what you do again, you start over again. You take the each point, each instance, and you measure the distance of each instance again to each cluster centroid. So you measure the distance from here to here, and from here to here. And since this instance is closer to this green centroid, you assign it to that. Okay. So you basically, and then once you're done with that step, again, you take the average of these green instances and move this cluster centroid to the average of these green instances. So that's what happens here. So if you go to the third step here, this was moved a little bit to right here. Okay, this was moved a little bit to right here. And this process, this iteration goes on. It continues on until these cluster centroids can't move anymore, until they can barely move. And basically that's when you stop and you're happy with the final cluster centroids of your model. So to repeat it, the first step is you initialize these centroids. How many cluster centroids, how many clusters you're going to have? It depends on your domain expertise. There are some techniques, and we'll discuss one of them today, that you can use called elbow technique to determine how many clusters you need. But if you understand the problem, I would highly recommend that you use your domain expertise to figure out how many clusters you need. If you have no idea, or if you don't know how many clusters you should start off with, I would definitely use some type of elbow technique that we'll discuss like today to determine how many clusters to start off with. And then even after you're done, I would just simply plot the result with the final cluster centroids to make sure the result makes sense. Always visualize your data at the end of your clustering to make sure it's in line with what you expect to see, and it's not something that is completely out of the picture. Now, it might give you a lot of information beyond your comprehension. So as long as you try to understand and think about what it gave you, it's fine. But always try to visualize the data, especially for problems that you understand very well and that it should look like this. And if the Kmeans clustering did not do a good job in terms of clustering, it simply means that you might need to add more features, or you might need to massage the data, add more mathematical equations to those features, or mathematical manipulation to those features, to get it in a format that Kmeans understand the problem much better. Okay, So now let me discuss this. Let me just say this one more time, just to make sure you understand. So first, you initialize, let's say in this case, 2 cluster centroids. You measure each instance to this cluster centroid and to this cluster centroid. And if the Euclidean distance is closer to this, then you assign it to that. So the Euclidean distance from this instance is closer to this cluster centroid. And that's why this point here, this instance, was assigned to this cluster centroid. Okay. And then you do the same thing for every other point. Then you take the average of all these instances within that cluster, and then you move this cluster centroid to the average. Okay. Same thing. You take the average of all these instances, you move this cluster centroid to the average, and then you start over again. Then you take, each instance and measure the Euclidean distance to each cluster centroid from here to here, from here to here, and then reassign these instances to green and red. And then you take the average of all these green instances, the average of all these red instances, and move the green and red cluster centroids to the averages that you just got. And then you just keep doing the same process until your model until these cluster centroids can't move anymore, or they just wouldn't move too much, and that these are considered your final cluster centroids. I hope this makes sense. So we talked about, what type of distances we have, and you can see we have Euclidean distance function. If you recall this from your algebra class, you probably had it in high school. It's just simply your xi minus your yi square. It's just x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. You take the square root of that. That is your Euclidean distance function, right? The Manhattan is a little bit different. And instead of using instead of squaring this, you just and taking the square root of that, you just take the absolute value. Okay, that's your Manhattan. And then your Minkowski distance function, again, you use the xi minus yi, and then you use this distance function to calculate your distance, basically. So, and in Python, when you use Python or whatever, language you use, you could be using R or Julia or anything else that you use to solve these problems, is, you have the options of selecting which type of a distance function you want to use for your problem. And you can play around. We can just use Euclidean and then compare it with Manhattan and to see the differences in results. But the differences shouldn't be too much, at least, depending on the problem, depending on the nature of the problem. So feel free to play around with different distance functions to see how much it changes the result of the clustering. Okay. So this is the distance function that I was talking about. And then we talked about the steps here: determine the number of clusters based on your domain expertise, the initialization of the cluster, and then and so on and so forth. Right? We discussed all of these steps in that picture that I showed you, right? But this is just for your own reference when you go back. So now, if you recall, I talked about determining the number of clusters. How many clusters are you going to use for your problem? Okay. So as I said, the best way to do this, if you don't know how many clusters to choose, is to run it with different number of clusters. Start with 2 clusters and go to 20 clusters, for example. Okay. 2 clusters, 3 clusters, 4 clusters, until you reach, let's say, 20 clusters. Okay. And then you calculate the inertia. There's this parameter called inertia. And inertia is also called the within cluster sum of squared errors. Within cluster sum of squared errors. And what it calculates, it basically is the minimum of the minimum of double absolute, of xi minus mu j. And what xi is each instance, and mu j is the mean of the sample in the cluster, okay? And basically, you kind of square that like afterward. And this is in vector form, right? This is in vector form, and this is called your inertia number. Now, if you remember from your linear algebra class, if you've ever taken a linear algebra class, this is your normalized Euclidean distance. The double absolute value is basically your normalized your normal for your Euclidean vector, basically, and that's what you're doing here. Okay, so if you plot this, if you plot the number of clusters on the x-axis versus sum of squared errors on the y-axis, at some point you're going to see an elbow curve, right? So you're going to your inertia, your sum of squared like errors is going to go down pretty drastically, and then finally it starts to level off. Okay, so it starts going down drastically, and then it starts to level off. You're trying to find that elbow point, which is in this case right here. See, you see this beyond this point here, your sum of squared errors, or your inertia, which is simply this equation here, is not decreasing as much. It is going down, but it's not drastic change, So you could have more clusters, you could add more clusters, but the issue that you'll face is that it's going to not pick too many samples within that cluster. So you're going to have cluster one with, let's just say you have a data set that has 10,000 rows of data. Okay, so you're going to have cluster one with, for example, let's just say you have a data set that has 10,000 rows. Okay, and then you apply this technique, and your optimum number of clusters, let's just say it's going to be 4. Okay, so what's going to happen is you're going to have cluster one with, let's just say, 500 samples, cluster two with, let's just say, another 500 sample, cluster three with, 499 samples, and cluster four with 498 samples. And then cluster, if you add more clusters, those clusters would have less number of, samples within them. So you're going to have cluster 5, for example, having, 5 samples or 6 samples. Cluster 6 having, 10 samples or 20 samples, as compared to the other clusters. So, and this is not always the case, but I'm saying, like, if you go beyond, if you add too many clusters, into your problem, then a lot of these clusters might have only a small number of samples within them. So that's why you can always use techniques such as the elbow method, which I'm just discussing right now, to figure out how many clusters you're going to need for your problem. Okay, how many clusters you're going to need for your problem. There are other techniques that I'm not discussing in this short course here that you can use to figure out number of clusters that you're going to need for your problem. But as I said many times by now, is use your domain expertise. Once you're done with clustering, visualize the data to make sure it makes sense. If everything makes sense, great. If you're happy with the final clustering result based on simple visualization, then you can move on to the next step. And a lot of times, you can use an unsupervised K-means clustering, for example, to label your data. And once you're done, once you're happy with labeling your data, you can move to the next step, which is, use that labeled data as your output to your supervised machine learning algorithm. You can use the labeled data from unsupervised technique and use that as the output to your supervised machine learning algorithm, which in those cases, they also call this a semi-supervised technique, semi-supervised, where you start with an unsupervised, and then you go to a supervised technique, and this is called a semi-supervised. And we discussed this in lecture 1, but I just wanted to touch on it one more time since we covered what K-means clustering is and how it works. So, so pretty simple, right? So the the concept, to be honest with you, behind K-means clustering is really all you got to know is simply just basic linear algebra and just a distance function calculation, which we covered, the Euclidean, Manhattan, and all those things, and the rest of it is simply taking the average and moving these clusters, So the concept is not that complicated. We're not talking about rocket science here, and the concept of K-means clustering is actually fairly simple, as long as you understand what is happening behind the scene. So with that being said, let's go ahead and do an example. Again, this is an example. So when we published the first book, Hydraulic Fracturing, chapter 24 was dedicated to just machine learning. And we wanted to include a couple of examples for, using machine learning to optimize completion design and using machine learning, unsupervised machine learning to for liquid loading problem, So we discussed those two problems in more detail in the book, but one of the examples that we gave at the end of the book to understand the mathematics, to understand the calculations behind K-means clustering was this. So imagine that you've done your clustering, okay? Let's just say you apply your K-means clustering based on the steps that I showed you, okay? And you have 4 attributes. You have gas rate, you have casing pressure, you have tubing pressure, and you have line pressure. These are your input features, okay? And then the output of K-means clustering would simply be, if you chose 2 clusters, which is loaded versus unloaded in this case, cluster 1 and cluster 2, you're going to have the output of K-means clustering is going to be a number for each feature. So gas rate, cluster 1 is going to be 4323. Cluster 2 is going to be 3923. Casing pressure, cluster 1 is 660 and cluster 2 is 2073. Tubing pressure, 571, and then cluster 2 is 600. Line pressure is 377 and cluster 2 is 479. So these numbers that you see for cluster 2 and cluster 1, these are the output of your final cluster centroids. These are the final cluster centroids for each feature, okay? And also you're given these features. You're given gas rate, casing pressure, tubing pressure, and line pressure. And you're asked, okay, tell me each of these new rows that you're given, row 1 has a gas rate of 4,500 MCF a day, casing pressure of 1,000 PSI, tubing pressure of 850, and line pressure of 500. Does this row fall under cluster 1 or cluster 2? So you can use this, you can actually use basic algebra that I'll show you in a minute to figure out where each row falls under. Is it going to fall under cluster 1 or is it going to fall under cluster 2? Okay. So you want to figure out first row, second row, third, fourth, and fifth rows. These are the input features you're trying to predict whether it's going to fall under cluster 1 or cluster 2. Okay, so just one more time, just to be very crystal, to be like crystal clear here. The top table shows you the final cluster centroids, okay, for cluster 1 and cluster 2 for each of these features that you have in your model. And the bottom table is basically, you're given this bottom table and you're tasked with, okay, tell me, based on this final K-means clustering model that you trained, where does each row of this data fall under? Is it going to fall under cluster 1 or is it going to fall under cluster 2? And that's what we're going to solve together here in the next couple of slides. Okay. So don't be intimidated by the calculation here. Okay. So first off, I'm using Euclidean distance function. That's what I'm using. I'm using Euclidean distance function. And I'm calculating, if you remember, the Euclidean distance functions is going to be x2 minus x1 square plus y2 minus y1 square, plus, and so on and so forth, right? So what I'm doing here, I'm taking 4,500 minus 4323 and then squaring that. Now, where the heck did I get 4,500 and 4323? So let's go back. Here's 4,500. I'm taking 4,500 minus 4,323. Okay. So I'm taking what I'm expected to predict, 4,500, and subtracting cluster 1 centroid for gas rate, which is 4,323. And then the next thing is plus 1,000 minus 660. Let's do, here's the next thing. 1,000 minus what? Minus 660. Plus 850 minus 571. 850 minus 571 square plus 500 minus 377. 500 minus 377 square. Perfect sense, right? You're trying to calculate the distance between each new row that you're given versus cluster 1. And you do the same exact calculation once you're done for cluster 2, which is the next slide that I have. So if I go back here, cluster 1 distance for row 2, cluster 1 distance for row 3, cluster 1 distance for row 4, and cluster 1 distance for row 4. So let's look at cluster 1 distance for row 4. It says 4,340 minus 4,323. 4,340 minus 4,323. Then it's going to be what? Then it's going to be 840 minus 660, right? 840 minus 660. Then it's going to be what? Then it's going to be 690 minus 571. Then it's going to be 500 minus 377. 500 minus 377 squared. Do the math, and you get a distance 490, 425, 363, and so on and so forth for each one of the rows that you have in your data. This is all, remember, this is all for cluster 1. So you have to repeat the same exact calculation for cluster 2 now. Because remember, cluster 2 centroids are different than cluster 1 centroids. Okay, so let's go back here. So now you can see cluster 2 distance for row 1, cluster 2 distance for row 2, cluster 2 distance for row 3, row 4, and row 5. And simply what you have again, you have 4,500 minus 3923. 4,500 minus, and instead of 4,323, now we're using 3923. And that's because we have moved on from cluster 1. We're going to cluster 2 now. Do the exact same calculation for cluster 2. Exact same calculation for cluster 2. Repeat it, okay? Then you get, 3170, 3223, 3277, and so on and so forth. Now, the final step is the last step. If the calculated distance for each row is smallest, assign the row to that cluster. In this example, the calculated distance for cluster 1, step 1, in each row is smaller than the calculated distance for cluster 2 in each row. So if you look at the results here, you have 490, 425, 363, 303, 245. All of these numbers are smaller than 3170, 3223, 3277, 3332, and 3388. So each one of the numbers, if you compare 490 versus 3170, of course, 490 is smaller than 3170. So that's why you assign that row to be clustered as cluster number 1. So you assign everything. So all of these points that you were given to predict, all of these rows will be assigned to cluster number 1 based on their distance measure. I hope this makes sense. I hope this clarified the concept a little bit more. So what we're doing here, as I said, we're not doing anything complex here. We're just using distance, Euclidean distance function, which is very famous, very well known, very widely used. and we're just calculating distances after your K-means clustering have been set and optimized. Any questions so far before we move on to the NumPy, using NumPy libraries, using going more into using Python? Any questions?
I don't think we have any question for now. You can continue.
All right, so we'll move on to the next section. So now that we understand, so far we've covered ANN, one type of supervised machine learning algorithm, and then we've covered another type of unsupervised technique, which is called K-means clustering. Now let's move on and talk about different libraries within Python. And then what I'll do, I'm going to show you how you can download Python on your computer. You can use, for example, Google Colab, stuff like that, to go in there and just write your codes and everything else from there as well. But I want you to I want to show you Jupyter Notebook and how you can use that to run your code and how you can save it and all those things starting next lecture. But I want you to first understand some of the libraries, and then we'll go and show you how you download Python, and then finish this lecture. And then next lecture, we'll go in there and do some coding together. Just want to make sure that you guys do download Python by next lecture. So that way you have it and you could code along with me. I'm going to code from scratch. You can code along with me. Just a few basic functions, a few basic examples within Python to kind of get you started. Okay. So first off, what is NumPy? And NumPy is a library, first off. Is a library in Python, is one of the fundamental package for scientific computing in Python. Okay? It's basically a linear algebra library in Python. You can see all this, a lot of these algorithms, without linear algebra, they wouldn't exist. So NumPy allows the linear algebra to run in the background, and it's basically it's a fundamental package for scientific computing in Python. Okay. Almost all the libraries in the PyData ecosystem heavily rely on NumPy as one of the fundamental building blocks, and is considered as fast that it has bindings to the C libraries. And it's considered fast because it has bindings to the C libraries. And so basically NumPy contains useful linear algebra capabilities. It has n-dimensional array objects. It has broadcasting functions. We'll cover some of the basics of NumPy. We'll import the library. You can import NumPy as NP, for example, import the library. Then we'll do some array and some basic calculation next lecture when I show you within Python. Okay, so just remember, if you take one thing from the slide here, just remember that NumPy is is one of the fundamental. Pretty much any problem that you want to solve in Python involves first importing the NumPy library. Not every problem, but a lot of the problems, especially if you're going to use machine learning. If you're going to use machine learning, you have to have NumPy library imported first if you're going to be using a lot of these calculations and a lot of these libraries that you have in Python. So if one thing you take from this slide here, just remember that NumPy is basically a linear algebra library in Python. It's a fundamental package for scientific computing in Python. And when you download Anaconda, so I'm going to show you how you can download Anaconda. Okay. And Anaconda is basically, and instead of going and downloading Python and installing, every single library from scratch in Python, what Anaconda has done, it has created this platform where a lot of these libraries have already been built within Anaconda. So when you open, Python in Jupyter Notebook interface or in Spider interface or whatever interface you choose, it has a lot of these libraries already installed. So you don't have to go into your command prompt and type in pip install this library. pip install that library. By the way, if you want to install a library that did not include with Anaconda, you can always do pip, like PIP, right here, pip install, for example, NumPy. In this case, you wouldn't need to, because we're going to download Anaconda, and Anaconda has has hundreds of libraries already built in and already installed. So there is no need for you to go in there and do pip install NumPy. You can do pip install NumPy, but it will tell you that NumPy library has already been installed and the requirement has already been satisfied. So you can do it. It won't do any harm to you, but there is no need, because Anaconda has already those libraries built in, okay? And I'll show you at the end of this lecture where to go to Anaconda, where to download it. Just bear with me for a second, okay? So pip install the library name that you want to install, if that library has not been installed within Anaconda. So if you use a different type of library that is not as commonly used, or is just not installed within Anaconda, you can simply do pip install that library, and usually it will install it for you. Otherwise, it will tell you what the problem is, and then you have to figure out, or you have to do a search online to see why it didn't. You might have to install a couple of other packages, or a couple of other items, download a couple of, other stuff prior to being able to install those libraries. But remember the command pip install this, pip install that, pip install this, pip install that. Just remember that, because we're going to go over that a little more detail. So as I said, NumPy arrays are the main ways we use this library throughout this course, which we'll show you a couple examples. NumPy arrays come in two forms, such as vectors and matrices. Vectors are 1D arrays, while matrices are 2D arrays. Okay, vectors and matrices, are 2D arrays, and we'll show you a couple examples next class. The next library that is very commonly used is called Pandas. Okay, Pandas is so powerful, and it has a lot of great functionalities, and it's just great for especially if you're starting out and you're used to Excel. A lot of people regard Pandas as the Python's version of Excel. Okay, as the Python's versions of Excel. So if you're used to using Excel a lot, which I'm sure everybody has by now, we all have these spreadsheets and all those things. Pandas is designed to work with like those type of data frame type of format, and it is an open source library that is built on top of NumPy. Okay, if you remember the previous slide, we talked about NumPy. So Pandas is built on top of NumPy. And it is basically a Python's version of Excel, and it allows for fast analysis, data preparation, cleaning. All this data preparation, cleaning, all those stuff can be done within Pandas. Remove this column, remove this row, add this column, add this row, do this simple math, this plus this times that, or more complicated math. All that stuff can be done within Pandas. And I highly recommend to get very proficient at it. There are classes that are just taught just for Pandas. What we did in the book that we published, the machine learning guide for oil and gas using Python, we actually have a lot of the functions, using the oil and gas summarized, within the Pandas library. You can go through them one by one and, manipulate the data, change the data around, do whatever you want to do with it. And a lot of times, I'm telling you guys, do not spend a lot of time on tedious tasks. If a task is tedious, you have to do a lot of manual stuff, don't do it manually. There's probably a function within Pandas that can do it for you like this. In one line of code, you're done. So if you have problems that you got to do manual stuff back and forth, copy and paste and this and that, those things can all be done using a couple of lines of code, either within Pandas or within Python. So one thing that I recommend all of you guys, and we can get started on this class, is to learn how to code. It's not something that is frightening. It's actually, a lot of people are just have anxiety from, oh my God, I'm going to code. It's not, it's actually, Python has made it so simple that anybody can learn. Anybody can really go in there and just, build their own functions and, do different type of data processing, preparation, and cleaning all within Python. So don't be afraid to dig into it, So if you download Python, as I said, itself, without downloading Anaconda, you might have to do pip install pandas. But if you download Anaconda, which will show you, it already comes with the pandas package because it's one of the most widely used packages. So pandas also has built-in visualization features as well. It's some basic stuff. There are other libraries that are much more powerful for visualizations than pandas, but pandas also has those built-in visualizations for some quick plotting and it has those. So just FYI, you can also plot figures and stuff like that using pandas. So the next one, which is the most popular plotting library in Python, is actually pretty powerful because it gives you a lot of flexibility when plotting different aspects of a figure. Is called Matlablib. Matlablib. Okay, that's the name of the library. Okay, so Matlablib is simply a visualization library in Python. It gives you a lot of flexibility. If you're that kind of a guy or that kind of a lady who likes to change certain things, the font size, this, and little aspects that some people don't care about. If you're so, focus on those little things, if you're very detailed, Matlablib would be great for you. Especially a lot of the engineers were very analytical. We like to have detailed stuff. I'm going to add a little font here, a little thing here, Matlablib is perfect for that. So use Matlablib. Okay, as I said, this Matlablib comes with Anaconda. If it doesn't, you can do pip install Matlablib. If you just simply go the Python route and go on Python's website and download Python from there, then you can do pip install Matlablib. Otherwise, Matlablib comes with Anaconda package. All you have to do just import the library prior to using it. By the way, we'll show you next class. Prior to using any of these libraries, you have to first import the library and then start using them. Otherwise, it will give you an error. It says, well, Python doesn't recognize this library. Or first you have to import the library to be able to utilize it. And check out this website, this matlablib.org. These are, again, all free open source sites you can go on. They have a lot of different guides that helps within there as well. If you're looking specifically to plot a different figure or specific figure, you can go to matlablib.org. And also just remember that if you guys are MATLAB users, it was designed to have a similar user interaction as MATLAB's graphical plotting. If you are a MATLAB user, if you're not, like I personally grew up with MATLAB, when I was in college, they taught us, when I was in college more than 10 years ago, they taught us MATLAB and all those things. But for you guys, the new generation, it's all Python, R, and Julia now. So, but if you guys are still MATLAB users, it was designed, just remember that it was designed to have a similar user interaction as MATLAB's graphical plotting. Okay. So that's math. So far we've covered NumPy, we've covered Pandas, and we've covered Matlablib. These are NumPy was linear algebra library, if you recall. Pandas was the Excel, the Python version of the Excel, for data manipulation, data analysis, and all those things. And then Matlablib is basically a visualization library. It gives you a lot of flexibility with different aspects of the figure and so on and so forth. The other one is called Seaborne. Seaborne is actually one of my favorite libraries in Python. And the reason I love it is just because it's so simple. Everything that you can imagine can be done with one line of code. You can do, import Seaborne as SNS to import the library first. And then what Seaborne has done, it basically has made a lot of these Matlablib figures that require a lot more lines of code. It's made it much simpler. You can do one line of code and plot a distribution plot, sns.distplot, and then put in your data frame name that you want to plot, and you're done. sns.boxplot, sns.joinplot, sns.thisplot and that plot. You can simply do one line of code, and it has made it so super simple. The visualization looks nicer. It looks better, in my opinion, than Matlablib. It's many data scientists' favorite visualization library. It's Seaborne, okay, and it does come with Anaconda, so there's no need for you to do pip install, Seaborne. There's no need for that because it does already come with Anaconda, okay, and it has a lot of nice default styles that are very user friendly to call and use. And it's designed specifically to work very well with Pandas. So SNS and Pandas go hand in hand. They're designed to go together very well. So highly recommend using Seaborne library for data visualization. Also, again, check out these websites. And I'm putting all these sources at the bottom just for your reference. These are all free, open source stuff for you for your education. There's no hidden marketing stuff behind us. These websites, just go on there, check it out, get familiar with it, understand it better, and then so on and so forth. So now, the last one that I want to talk about is the Plotly. Plotly is another great visualization library. Now, the beauty of Plotly is that it is interactive. So what I mean by interactive is if you hover over it, it will show you the numbers. You can zoom in, zoom out. The figures look much cleaner, much nicer. If you're trying to build an app, build a platform, build a dashboard, you can actually combine Plotly with Dash. This is another library that we won't have time to discuss, but we can combine Plotly and Dash to combine together and build these really nice dashboards, for any organization that you work for. We actually covered, again, Seaborne, Plotly, and Plotly, all of those in very much detail in the second, or I think it was the second or the third chapter of the book, how you can build different dashboards, make different plots from start to finish, and highly recommend it. Again, check out this website here. Check out this plotly.ly to get more information on it. But Plotly, I believe, if I'm not mistaken, it does not come with Anaconda. Okay, when you download Anaconda, you have to do pip install Plotly and pip install cufflinks. Okay, these two, make sure you first install them. Otherwise, if you use Plotly, it will give you an error. So first do pip install Plotly, pip install cufflinks. Even if you have downloaded Anaconda, which I'll show you in a minute, you still have to do pip install Plotly and cufflinks to make sure these libraries would work when you install them within when you import them to Python. Okay. So with that being said, I'm going to stop right here. I'm going to go on and show you how to download Anaconda. And what I want you guys to do is to download Anaconda prior to next class, okay? Make sure to download Anaconda prior to next class so we can, do an example together, go through some lines of code. I'm going to show you the Jupyter Notebook, how the interface is set up, some of the shortcuts and short keys that you can use to kind of get started with Anaconda. So, but I want you to first, at the end, to just do it as soon as possible. Don't wait till last minute. Okay, it should take, to download Anaconda, it takes about maybe 30 minutes because there are a lot of pre-built libraries within Anaconda. So download the library, download Anaconda package. And let me share my screen first. So let's see. Let me do this real quick. So can you share? Let me see if you can see my screen. Can somebody confirm? Can you guys see my new screen now? Can you guys see this? Just yes or no?
Yes, we can see it very well.
Perfect.
Yes.
All right, just go to Google, okay? Google.com. Type in Anaconda download. Anaconda, Anaconda, download. Okay, Anaconda download. Click on that. And you can see here it has Anaconda. Click on Anaconda. And then you can read about it, your data science toolkit. It's an open source and so on and so forth. Go down here, go at the very bottom. The very bottom, it depends on what you have. I have, a Surface laptop, it's a Windows 10 that I have. If you have a Mac, if you have Linux or Macintosh, whatever you have, you can see here, download I have a 64-bit graphical installer, so that's what I use at least. And this is the latest version. Download Python 3.8, the latest and greatest version. It has all this stuff in it. Don't download. I wouldn't recommend downloading previous versions for this, at least for the purpose of this course. So just simply click on this. If you click on it, this extension, this executive file will pop up. It will take, in this case, 2 minutes. But I already have Anaconda installed on my computer, so I don't need to do it again. But simply, once this is done downloading, click on it and just go through the default next. And then you'll be good to go. I mean, it's going to take you probably 30 minutes. Be patient. There's a lot of libraries that will be downloaded. And then pretty much once you're done, then you are good to go for next class. And then we'll go over the fundamentals next class and do an exercise together in next class. So with that being said, that's all I had for today. I just wanted to give you an example on unsupervised, go through some of these libraries, and then cover some of these libraries in next class. So with that being said, if you have any questions, as I said, feel free to, if you have any questions, always you can send me an email. I have my email, Belyadi@observeintelligence.com. I'm on LinkedIn. Also, make sure to subscribe to the podcast that I mentioned before. But if you have any questions right now, I'd be more than happy to take your questions.
Thank you, Mr. Belyadi, for this informative session.
Yeah, you're welcome.
One of the questions is from Ayman about neural networks. How many neural and layer at least need to solve any problem in petroleum engineering? For example, can we do it by 3 neural and 1 layer?
Mm-hmm. Yeah. So the question is, how many neurons and how many layers do we need? To be honest with you, the answer to this question is a function of your problem. The more complex your problem is, the more neurons and the more layers you're going to need. If you go beyond 1 layer, now we're talking about deep learning, right? So when you have a lot of layers, it helps you pattern recognition, right? That's what deep learning does. So there is no there is no equation or answer. For example, you got to use 10 neurons and 1 layer, or there's no recorded equation that you can use to figure out how many neurons you need. So what I recommend you to do is, if you have, it depends on how much data you have. If you have, let's say, 1,000 rows of data, not much data, and you're trying to really apply a neural network, start with 10 neurons, go to 20 neurons, and go to all the way to 100 neurons, and then keep increasing the number of neurons to see if your testing accuracy improves or not. If your testing accuracy doesn't improve, then you don't need that many neurons. But the answer to your question simply depends on the type of problem you're trying to solve. If the problem is complex, if you have a large data set, you need more neurons to extract information from those features. And then as far as layers, I personally believe that a lot of the problems that are simpler, especially in the oil and gas industry, can be solved with 1 or 2 layers. But there are some problems that are more complex. You might need more number of layers, to solve those problems. So as I said, the easy problems you can solve with less number of neurons and probably one layer. The more complex problems, you're going to need more layers and more number of neurons. So there is not, I wish I could give you an equation. Here's the equation, 2x plus 1. Do you use this? There is no such an equation. I have not heard of that. It doesn't exist simply. And it's just try and error. And you have to try different neurons to see what improves your model accuracy. And basically, one of the approaches is grid search. As I said, taught last time, grid search optimization, run different combinations of neurons and layers using grid search to see what comes out as the optimum number of neurons and layers using grid search optimization, as opposed to just guessing or doing manual work.
Okay. Another question. Can you give an example on how to use ANN or unsupervised for equation of states, and why ANN is favorable for equation of states?
Can you give an example on how to use ANN or unsupervised for equation of state? So if you're talking about, I'm a little bit confused, who said that ANN was favorable for equation of state? I mean, you can really use, here's the thing, ANN is just one algorithm out of many algorithms. You have so many different algorithms when discussing this class. You can use support vector machine. You can use tree-based algorithms like random forest, extra trees. You can use boosting algorithm, gradient boosting and adaptive gradient boosting and all those things. You can use, simply multilinear regression or k-nearest neighbor, or there are so many different algorithms that you could use. And I cannot, without seeing the data set, without seeing the problem and the features, I could not simply sit here and say that this is the best algorithm to use. The type of problem that you have dictates what type of algorithm to use. Just remember that ANN is one type of machine learning algorithms, and there are so many other kinds that could possibly provide you a much better answer. The answer is not always in using neural networks. A lot of the tree-based algorithms could provide better accuracy, depending on the type of the problem, the nature of the problem. So all I'm trying to say is that there's no such a thing as ANN would be the best algorithm. And there are so many other algorithms that we did not discuss in this class. This is the kind of class that I usually teach in 5 days, 8 hour, like a day course. To summarize it in 4 hours, I would have to pick one algorithm and focus on those and talk about those. But just remember that depending on the nature of the problem, that's what dictates what type of machine learning algorithm to use. And until I see what kind of input and output features you have, what your problem you're trying to solve, I wouldn't be able to give an exact answer as far as what's favorable and why is it favorable as compared to the other algorithms.
Okay, that's pretty much it for the questions. Thank you again, Engineer Belyadi, for your valuable time.
Yeah.
Next lecture will be on 28 on the same time, 9 a.m. on Texas time. I would like to remind you to finish your quiz before the deadline, and this session is being recorded, so it will be posted on PyPetrol YouTube channel. Stay tuned for the other upcoming webinars by following Arab Oil and Gas Academy Facebook page. We wish you all the best of luck and a fruitful day. Till next time. Bye-bye.
Thank you.